Okay, so here you have the topics, vibration and sound. The overview: explain how vibrating objects produces a sound wave. Discuss reflection, refraction, diffraction, and interference of sound. Discuss the speed of sound through different media, and explain loudness and pitch, and define resonance. Okay, so there are two classes of waves: mechanical and electromagnetic waves. In this discussion, we're going to be looking at mechanical waves, which sound waves are. Um, and depending on the media that the sound waves pass through, a solid, liquid, or a gas, there's an effect. The effect is the speed change. Um, so mechanical waves must have a substance to travel through. Mechanical waves traveling through a medium consist of vibrations being passed on from one molecule to another. And a traveling wave, either mechanical or electromagnetic, is a disturbance that travels out from the source, producing it, transferring energy from the source to other places through which it passes. Okay, so just on a couple of things there. Electromagnetic waves differ from the mechanical waves that we've just talked about. Electromagnetic waves being radio waves for transmission of radio signals are light waves, if you like, from the sun. These would be examples. X-rays, these types of waves are known as electromagnetic, where sound waves differ to a certain extent in that they need a media. They're a mechanical wave anyway, and they need a media or a substance to travel through. The light from sun travels through the vacuum of space, and so it doesn't actually need a medium for it to pass from itself to the Earth and the other planets, etc., etc. A traveling wave is distinguished from another type of wave called a standing wave. The traveling wave is the one that you take for granted, that you're most familiar with. And basically, it just means a disturbance that travels from the source, i.e., for instance, let's just say the sun, to the earth. It transfers the energy from the source to other places through which it passes, and the sun would be a perfect example of that, even though that's an electromagnetic wave. But nonetheless, as opposed to a traveling wave, differs to another type of wave called a standing wave. And standing waves where two sets of wavelets pass through one another and they create the effect of a wave at that point, and that's called a standing wave. A traveling wave is different from that. Okay, a transverse wave is really, really simple. Basically, all that it means is that the vibrations are in the y plane, i.e. in the up-down direction, but the direction of the energy, the propagation of the energy, is at right angles to that. It's to the right in this case that we have there. A longitudinal wave is very simple as well. I mean, basically, all this means is that the vibration is from left to right, and the direction of the energy transfer is also in the same direction, i.e., it's along the x-axis in this case. Okay, so the vibration is left and right, and the direction of the energy is also along the same plane, along the x-axis. So you get a moving compression wave is what you have here. Compression's here, and the expansion there is called a rarefaction, and that is equivalent to a wave, and that is what a sound wave is. Okay, and some of the terminology that you need then around these particular types of waves, and then the sinusoid waves. Well, there's a couple of things. You need the wavelength, first of all, is probably the most important thing. And the wavelength is defined as a start point to the identical start point, the next identical start point. So, for instance, from crest to crest, or from trough to trough, or indeed from the equilibrium position. Okay, this one's a bit trickier because it's the equilibrium position but on the up in this case. So you need to find the next equilibrium position and on the up. So that would be a wavelength from there to there, but not from there to there, because this is on the down. The slope is in the from left to right. It's decrementing. And then This is called a cycle then, from, let's say, crest to crest. That's known as one cycle, which links in then to the definition of a hertz, because 1 hertz is 1 cycle per second. Okay, so that's where that comes in. And as I said, this is the equilibrium position. Point to remember if in some of the questions in the tutorial, loudness depends on how high this is here, the amplitude. Okay, so the taller the wave, the louder the sound. That would be the idea there, as opposed to the closer these points are to one another. So if this point here is squeezed all the way back very, very close to the green, that would increase what's called the frequency, and that would make the sound appear much higher pitch or a higher frequency. So the closer, or the higher the frequency, the higher the pitch, and the bigger the amplitude, the louder the sound. And there you see a couple of the points that are brought up. Particularly, 1 cycle per second is called 1 hertz, as opposed to if it was 2 cycles per second, that would be 2 hertz, etc. 10 cycles per second would be 10 hertz. And the distance traveled by 1 cycle in 1 second is called the velocity of the wave. Okay, so since sound waves are longitudinal waves, we need to just look at the terms. In a longitudinal wave, it consists of a compression and a rarefaction. So compression is where the particles are compressed together as the sound energy passes through a point, and then as the sound energy passes that point, you get a spreading out, and that's called a rarefaction. And the distance, and I'm guessing that this wavelength should actually stop over here, because a full wavelength is the compression to the rarefaction. Okay, and that's a full wavelength. This is a nice example here then, a simple way of demonstrating how sound is created. The vibration of a ruler and just moving the ruler in and out then, we've all had the experience, look at that if you move the ruler to the edge and vibrate it, you get a slow vibration. If you pull the ruler back the way, you get a fast vibration. The vibration has got to be greater than 20 hertz before a sound is created, and this can be tried, it can be demonstrated. Every source of sound is a vibrating object, a vibrating string in this case, and indeed another vibrating string in a piano as well. And the audible range is between the frequency limits of 20 hertz up to 20 kilohertz, which also gets a mention in the tutorials as well. Infrasonic waves are frequencies below the audible range, and ultrasonic waves are frequencies above the audible range. Ultrasonics are important then in medical devices and inspection techniques. Nothing too difficult here. We've got our vibrating tuning fork. Causes a vibration of the gas molecules between the tuning fork and the human ear. And what happens is that the gas molecules of the air, once the vibrational energy from the tuning fork passes through the air and into the ear, it causes the eardrum to vibrate, and this causes a mechanical effect, and so you get the effect of sound, and it's interpreted then in the brain. Probably a better diagram then will be this one here, and we have a loudspeaker and we have the ear, and we have numerous molecules of air, and basically what we have is we have the sound wave passing through the air, and what you've got is compressions here. You can see where the air molecules are very close together, and here where the air molecules are quite far apart, and so this represents a full wavelength from a compression to a rarefaction. Okay, and that represents our wavelength. Another neat little diagram, but this time we've got a sinusoid then superimposed on the whole thing. So we've got our loudspeaker with our compressions and rarefactions again, and you notice that from peak to peak is our wavelength, and that represents, for instance, a compression to a compression. Okay, so it's very straightforward again. A peak represents compression, and a trough represents a rarefaction. But altogether, from compression to compression, it represents one cycle or one wavelength.